Thank you, Trevor. My name's Steve Trainoff, and I'm the Chief Scientist at White Technology Corporation. And I'm joined here with Stepan Podzimek.
My name is Stepan Podzimek, and I am head of Department of Analytical Chemistry at R&D company Sinpo.
So we're going to talk today about some improvements in viscometric detection. And so the title of today's webinar is Advances in Viscometry, Extending the Detection Limits of Intrinsic Viscosity and Hydrodynamic Radius. So first, a quick outline, give a little background of why would anyone want to measure intrinsic viscosity, and then we'll segue to talk about the technology and improvements that we've made in the last few years about how to get really much better accuracy than has been achievable in the past. Then we'll talk about applications including a comparison of universal calibration with multi-angle light scattering, with applications to polymer conformation, branching, and then we're going to end with an example of measuring hydrodynamic radius and how you can use viscometry to really understand non-ideal SEC column elutions. And now I'm going to turn it over to Stepan for the background.
Yeah, so we focus on the determination of intrinsic viscosity. Intrinsic viscosity is one of the fundamental properties of polymers that gives information about polymer chain conformation and interaction with the solvent. Intrinsic viscosity is calculated as specific viscosity divided by concentration at concentration approaching zero. Specific viscosity, according to Einstein, is directly proportional to the volume fraction of polymer in solution. A traditional way of measurement of specific viscosity was using capillary viscometer that we can see on this slide. And specific viscosity was measured based on the time that is needed for polymer solution to flow through the capillary from one mark to another. And the time is then related to the time of pure solvent. Example of the determination of the intrinsic viscosity by capillary viscometer is on this slide. The slide shows the relation between specific viscosity divided by concentration against concentration. And the data are extrapolated to zero concentration, and the intrinsic viscosity is obtained from the intercept as indicated by the arrow. The applications of online viscometry are shown on this slide. The traditional application of online viscometers was in size exclusion chromatography with so-called universal calibration, and that was used to get molar mass distribution of polymers. Another application is measurement of the polymer size, and mainly it is the hydrodynamic radius, or it can be also the root mean square radius. More information can be typically obtained from so-called Mark-Houwink-Sakurada plot, which is a relation between intrinsic viscosity and molar mass in double logarithmic scale. The information about the polymer chain conformations are obtained from the slope of this plot, which is called exponent of Mark-Houwink-Sakurada equation. The slopes typical for linear molecules in thermodynamically good solvents are around 0.7. If we change from thermodynamically good solvents to poor solvents, then the slope drops to 0.5 because there is no effect of excluding volume. Oligomers, that is polymer molecules with lower molar mass up to roughly about 10,000 gram per mole, has the slope 0.5. Hard spheres, the slope is equal to 0. And the slopes larger than 0.7, typically between 0.8 and 1, indicate extended chain conformation. What is also very important that Mark-Houwink-Sakurada exponent can indicate branching because it decreases its increasing degree of branching. And linear polymers typically have linear Mark-Houwink-Sakurada plots, and the curvature of the Mark-Houwink-Sakurada plot indicate branching.
Oh, thank you, Stepan. So as Stepan pointed out, the traditional method of using viscometry is tremendously improved if one can couple it to a fractionation technique such as size exclusion chromatography. And if you, some early techniques where people have tried to do this is to put in line with the size exclusion column an online capillary viscometer similar to the one that Stepan described. And in principle, it's very straightforward. You push the sample through a capillary. You measure the pressure drop across the capillary instead of the time required to go through. And this works fine, but there's one problem. If you do this experiment, the pumps, which flow the sample through the system, have pulses, and the pulses for a very good pump is maybe 1 part in 1,000, but these pump pulses look just like signals. So in this plot here, on the blue is the measurement of the pressure across that capillary, and you can see there's a peak. The red line is the same measurement of a concentration detector. So we have a sample coming through, but it is obscured by the pump pulses. So you're limited to the quality of the pumps, and like I said, a very good pump can give you maybe 0.1% pulsing, but at that level, that limits your ability to measure the change in viscosity to that level of about 0.1%. Well, you can do better by using a bridge viscometer, and this has been used for maybe 20, 25 years. And the idea of a bridge viscometer is it has the ability to cancel pump pulses. So in a bridge viscometer, we enter the sample through the top, and now instead of having one capillary, we have 4 that are arranged in this bridge. And at the top, the sample splits into the right side and the left side. It flows through, and on the left side, we have a very large volume that has essentially no pressure drop across it. It's just a storage. So the sample goes in, but previously this has been filled with solvent. So when the sample comes in, it gets held up, and solvent comes out. And so when the two flows recombine at the bottom, you can see the blue is the solvent and the red is the sample, and you get a bridge imbalance across a pressure transducer called the differential pressure transducer, DP. And you can show fairly straightforwardly that the specific viscosity, which is the fractional change in the viscosity due to the sample, is related to the pressure across the bridge, DP, and the pressure from top to bottom of the bridge, IP, through this relation 4 dP over IP minus 2 dP. Now, the advantage of this is that the symmetry of the bridge means that it, to a great extent, cancels the pump pulses. So if you have a pump pulse, it shows up on the right side of the DP and on the left side of the DP approximately equally. So since the differential pressure is, if the pressure on both sides are going up together and down together, there's no difference between them. And so the differential pressure is mostly immune to the pump pulses. Now, one side effect of the bridge is that the sample goes into this holdup volume, and you have to wait for it to come back out again before you can make another chromatography injection. So let's talk about how well that works. Now, remember, the benefit is we're going to have the ability to cancel pump pulses. So here's a real measurement of a 4-capillary viscometer. In the blue is the pressure from the top to the bottom of the bridge, the so-called IP pressure, and in the red is the differential pressure that's across the middle of the bridge. And you can see the blue one trace on the right axis has about 7 psi, and the red trace, as advertised, is around 0, and that's because of the design of the bridge. But there are pump pulses, as you can see in the traces, and the pump pulses on the DP signal are much smaller. They're suppressed by a great amount, but they're not 0. So to characterize this suppression, we define a suppression ratio, which is simply just measuring the amplitude of the pump pulses as seen by the the IP transducer, which measures from the top to the bottom of the bridge, and then compare that to the pump pulse amplitude of the DP transducer. These are defined as IPA and DPA, and taking the ratio gives a measure of how much we're suppressing pump pulses. Now, if we did a perfect job, the DP pulses would be 0. And so the way this suppression ratio has been defined, if DP were to be 0, you'd see that the ratio goes to infinity. So if we have a perfect suppression, then this suppression ratio would be very large. But in fact, with a real bridge, it's only about 25 to 1. And that improves over the single capillary inline viscometer by about the same amount. So you can measure the sensitivity to specific viscosity down to 3 times 10 to the minus 5. And that corresponds to being able to measure lower concentrations and lower pressures and therefore lower concentrations of smaller molecules. So that's great. The question is, why is it limited to 25 to 1? Why can't we do better? And for many years, this was not widely appreciated, is that the symmetry of the bridge, namely if you think about without that big holdup volume, it would be perfectly symmetric. You'd have 2 capillaries on the top and 2 capillaries on the bottom, and you should get perfect cancellation. But once you put that holdup reservoir, it affects the balance of the performance of the bridge in perhaps a surprising way. What we discovered in the last couple of years is that this bridge design, which has been used for a long time, is really limited by this large volume in the holdup reservoir. Namely, the fluid in here has a very small amount of compressibility. So when you get a pump pulse, the pressure on the left side that has the holdup reservoir is changed by the fact that the fluid goes into the holdup reservoir, but it gets compressed a little bit. So it's almost as if this is like a little spring where the holdup reservoir volume changes ever so slightly when the pressure changes. And that's not properly balanced on the other side of the bridge, and that's what limits the performance of this bridge. And so for many years, people have gotten very good data with 4 capillary bridge viscometers, but they were limited by this effect. And traditionally what people would do is they would use electronic filters or software filters to simply try to smooth out the pump pulses so that they don't see them. And that has, unfortunately, the side effect of also smoothing out the peaks that we're trying to measure. Now, what we realized is that it's fairly straightforward to balance this compressibility by adding another element to the 4 capillary bridge viscometer. And that's what we call a compensation volume. And it's in line with the pressure transducer, but it's not in the path of the sample. The sample goes through the 4 small capillaries, but it doesn't go through the compensation volume. But the compensation volume does act like a spring that has compressibility, that balances the compressibility in the delay reservoirs, and that really gives you a much better ability to cancel pump pulses. And so here is a plot. On the left side is the suppression ratio, and on the bottom is the volume inside the compensation volume. And we already had one point on this plot. We talked about when there is no compensation, you get about 25 to 1 compression, and that's way off on the left of this plot. It's actually off the screen. But as we increase the volume in this compensation volume, you can see what happens is once we balance the compressibility of the holdup reservoir, then the suppression ratio skyrockets to about 200 to 1 or even higher, depending on how well it's compensated. And that really boosts the sensitivity of the instrument without the need for smoothing out the data to hide the pump pulses that are limiting the performance of this type of measurement. And so that really pushes the sensitivity down to about 3 times 10 to the minus 6. Okay, so what can you do with this improved sensitivity? Well, you can measure smaller molecules, you can measure lower concentrations, but this all works well so long as the bridge is perfectly balanced. And what I mean by that is we talked about its susceptibility to pump pulses, but the signal itself depends on how well matched these 4 capillaries are. So we've got 2 capillaries on the top, 2 capillaries on the bottom, and by design you want them to be all exactly the same flow impedance so that they have exactly the same pressure drop. And that's what we call a balanced bridge. And historically what people did is you'd build a bridge, you'd measure how perfectly balanced it was, and then you'd get out with little files and you'd cut a little length of tubing and you'd put it in series with one of these in order to make it perfectly balanced. And that's great. So as long as it's perfectly balanced, and when we build an instrument in the factory, we balance it very well. But over time, as the device is used, you would slowly build up sample or dirt on the inside of the capillaries, and the pressure drops across these would drift slightly over time. So bridges work really well so long as they remain in balance. The problem is they can get out of balance. And we know when bridges get out of balance, bad things can happen. Okay, so we found a solution for this as well, and this is another innovation in this device, is that it would be really nice if we could automatically balance the bridge without having to take it apart and cut and file and adjust capillary lengths. And so we want to do this without cutting and without opening and doing service. And what we realized is that you can balance this without doing any modification to the flow design, as long as you can control the temperature of the capillaries. Now, I didn't talk so much about performance limits, but it's critically important that all of the capillaries are held at exactly the same temperature. This viscosity is a very strong function of temperature, and we're trying to look at changes in the viscosity down to a few parts per million. And for example, water has a change in viscosity of 2% per degree. So if you don't hold the temperature of the 4 capillaries accurate to within, say, 1,000th of a degree, you're going to be limited by temperature. So what we do is we hold all of the capillaries, except for the lower left one, in a thermally controlled spool at 1 temperature, and we change the temperature of the last arm of the capillary. And that's shown schematically with this little fire icon. Of course, we can heat and cool. Now, the nice thing about doing this is that the sample does not go through this capillary. This is on the end of the holdup reservoir, and during the measurement, we have sample that runs through the other 3 capillaries, but in the holdup reservoir, only solvent's coming out. So during the measurement, the sample doesn't see this temperature-regulated volume, but the solvent does. And so by changing the temperature of this independently of the other 3 capillaries, we can change the balance in situ. And there's no moving parts, there's no sliding seals, there's no cutting, and there's no tuning. So the way this works is I have a graph here of the tuning operation in practice. And on the left, we have the pressure drop as measured by the DP transducer, which is in the middle of the bridge. And it's in the black line, and you can see that it's round, it's not 0, it's minus 0.017 or so. The first thing that we do is we open up some valves in order to short across the DP transducer and find out what the real 0 should be. And that's this right here, which we call the target pressure. So we open up some valves. We say, okay, this is the pressure we want it to be perfectly balanced. On the right axis, we have the temperature of this tuning capillary. And it starts out around 25 C, and it's in the red curve. And then we start ramping the temperature of this tuning capillary, and as advertised, it affects the balance. So the DP transducer begins to follow it. As soon as the DP transducer gets to the target pressure, we stop ramping the temperature of this tuning capillary, and then we hold it constant during the measurement. So you do this, once on a periodic basis whenever the system gets out of balance, and that guarantees that you can keep the system balanced 100% of the time to get optimal performance. Okay, so the way this is realized in terms of a real device, that was all great in terms of schematics and cartoons, but this is an outline of the instrument that we have designed called the ViscoStar 3. And it consists of the same design, but with a lot more plumbing in order to make it into a real instrument. There's some heat exchangers, and at the very top of the system before it enters the thermal box, we measure the pressure, and we have a series of valves that will protect the system in case there's an overpressure. It goes through another heat exchanger to make certain it's very precisely controlled, and we hold the temperature of the bridge accurate to about 1,000th of a degree, and they're all tied together into a thermal block. That's the sample splits, and there are the 2 arms on the upper side of the transducer, the upper side of the bridge. Then we have the delay reservoirs that I talked about, these hold-up reservoirs on the left side, and we have a measurement capillary on the right, and this is where the bridge imbalance comes from. Then the sample goes through the out of the system. And so that's what it looks like in terms of schematic. And this is what the hardware looks like. The sample comes in from the left, We have a cross-flow heat exchanger that brings it to the right temperature. Then the measurement bridge is this copper block that has all of the capillaries soldered into it, and it's on a thermally regulated stage, and that's key. This is the series of delay columns that hold up the sample during the measurement. Then we have that tuning coil I was talking about that's independently regulated. There's a PLGA controller that will adjust the temperature of this in order to keep the system balanced. The measurement transducers are in these two areas here. And then that is the compensation coil that does the pump pulse cancellation. And that's the volume, and we adjust the volume by using different lengths of coil. And then what I said is also it's critically important to hold the temperatures constant and uniform during the measurement. So we have temperature control on both front and back of the bench to make certain that there's essentially no linear gradients in the system. Okay, so I'm going to turn this back over to Stepan to talk about what you can do with this device. And Stepan, please.
Okay, thank you, Steve. Now we come to various applications of online viscometer. This is the first application that is so-called universal calibration to get molar mass distribution of polymers. The left plot shows relations between molar mass and elution volume for various synthetic polymers. And as can be expected, there is a great difference between particular plots. If we plot instead of molar mass, the product of molar mass times intrinsic viscosity, the plot starts to overlay. That means we get calibration dependence that is universal for all polymers. Next slide shows the comparison of universal calibration with multi-angle light scattering detection. The graph shows molar mass versus elution volume. Plots obtained by SEC with SMALS, that is in a red color. And then in blue color, we have the plot obtained by universal calibration. The overlay is fairly good, but there is a difference at very beginning and very end of chromatogram. And this difference is then well seen on the distribution plot. So this slide shows a comparison of cumulative distribution plots obtained by mouse and universal calibration. And the plot from universal calibration is shifted to both high molar masses and lower molar masses. And generally, the universal calibration provides a broader molar mass distribution than SEC with a mouse detector. And this is mainly because of band broadening in the columns. Another drawback of universal calibration when compared to mouse is that the results typically depend on the columns that are used. Left graph shows distribution plots obtained for the same sample, but using different column systems. And the difference of molar mass averages, especially weight average and Z average, is quite significant. If we analyze the same sample using the mass detection, then the results are completely independent of the columns that were used for SEC separation. So generally, we can say that universal calibration is valid, it works, but the results typically depend on performance and type of SEC columns, because there is strong effect of band broadening, and the method cannot be considered to be absolute because there are still standards that are involved. We first have to measure polymer standards, and then we just can calculate molar mass. But it's also worth mentioning that the results are strongly dependent on size exclusion separation effects like enthalpic interactions with the column packing. And this is different to moles because in case of moles we get at least weight average molar mass correctly because it is calculated independently on separation performance. Now we come to a relation between the intrinsic viscosity and molar mass. This relation is very simple, and it is called Mark-Houwink-Sakurada equation. K and A are constants for given polymer, solvent, and temperature. And historically, this equation was used to get molar mass. It was viscosity average, close to the weight average. And if this equation is expressed in graphical plots, that means we plot intrinsic viscosity against molar mass in double logarithmic scale, we get Mark-Houwink-Sakurada plot. And this plot bears information about polymer conformation, about thermodynamic quality of the solvent. It is also very sensitive for polymer branching. And traditionally, the Mark-Houwink-Sakurada plot was obtained by polymer fractionation, typically using precipitation fractionation. So polymer was separated into 10 to 15 fractions. That was narrower compared to the original polymer. And then the fractions were characterized by capillary viscometer to get intrinsic viscosity and by membrane osmometry or preferentially by static light scattering to get weight average molar mass. And it required typically several weeks to get the plot for one sample. So using SEC, its online mouse and online viscometry, we can get the Mark-Houwink-Sakurada plot for one sample in less than 1 hour. Another application of intrinsic viscosity is the measurement of molecular size. It is, first of all, hydrodynamic radius. Hydrodynamic radius is radius of sphere that would have the same intrinsic viscosity as our polymer molecules. The volume occupied by polymer molecule in solution is called hydrodynamic volume, and it is directly proportional to the product of intrinsic viscosity times molar mass, and then using well-known equation for the volume of sphere, we can calculate hydrodynamic radius. Root mean square radius is typically obtained by multi-angle light scattering from the intensity of scattered light as a function of angle. But it may be just worth mentioning that the root mean square radius can be also calculated from the intrinsic viscosity and molar mass using so-called Flory-Fox equation. Now I would like to show a couple of Mark-Houwink plots and their application for the characterization of synthetic and natural polymers. In this graph, we can see 6 Mark-Houwink plots. The 3 plots colored in red, blue, and magenta are perfectly linear with the slopes close to 0.7. And I would like to emphasize that the plots are linear because they should be linear. By theory, the Mark-Houwink-Sakurada plot for linear polymers is linear, but we can also see Mark-Houwink-Sakurada plots slightly curved, even for linear polymers, and I think that the linearity of the plots is good evidence of the performance of the new ViscoStar. Then we can see in the region of lower molar masses, Mark-Houwink-Sakurada plot in cyan, and the slope is 0.5. And that is exactly what we should get because the molar mass of this polymer is from about 1,000 to, let's say, 15,000. That means that the molecules are short and they are not affected by excluding volume effect, so that we should get 0.5, and we really get 0.5. Then we have two Mark-Houwink plots that are in green, and they are shifted significantly to lower intrinsic viscosities compared to the plots of linear polymers. And this shift, this very low intrinsic viscosity, indicates highly compact structure, high density of polymer coil. And the slopes are close to zero. And if we remember the slopes for various molecular structures, we know that the slope for hard spheres is zero. That means that these molecules have very compact sphere-like structure, and indeed these polymers were prepared by group transfer polymerization, and they were prepared like star branch polymers with very high number of arms, and as you see, its mass and online viscometry really proved this structure. Next slide shows Mark-Houwink-Sakurada plots for copolymer of lactic acid and glycolic acid. These materials are used in pharmaceutical industry as a drug delivery systems and also for manufacturing of various medical devices. And this is a nice example how copolymer composition changes the interactions with the solvent. That means that polymers of different composition interact in different intensity with the solvent, and that results in contraction or expansion of polymer chain, and that this can be nicely measured by Mark-Houwink-Sakurada plot. And next example is for biopolymers, for polysaccharides. They both have relatively low molar mass, and the slopes are significantly different. So if you look at the plot of Dextran, the slope is 0.53, so it's close to the value that we would expect for oligomers, and indeed a significant part of sample has molar mass below 10,000 gram per mole. That means that they are short and they are expected to have slope 0.5. But this trend continues even for higher molar masses, and that is probably due to branching, because Dextran is branch polysaccharide. That means that for higher molar masses we have effect of branching, and that means that the entire slope is 0.5. And then we have heparin with very low molar mass. The majority of polymer has molar mass below 10,000. So we would expect again the slope close to 0.5, but we have almost 0.8. And the explanation for this behavior is that heparin is a charged polymer. Actually, it is probably the most charged polysaccharide, and the polymer chain is expanded by electrostatic repulsive forces, and then we get evidence of rod-like polymer chain conformation. Next slide shows the effect of branching on 4 polystyrene samples. So linear polystyrene is in red. The slope is linear. The plot is linear with the slope close to 0.7. So that is exactly what we expect for polymers for linear polymers in thermodynamically good solvents. And then we have shift of the plots towards lower intrinsic viscosities, and also the decrease of the slope, and the plots also become to be curved, and it nicely corresponds to the increase in amount of branching agent, which was in this case divinyl benzene. This is example of Mark-Houwink-Sakurada plots for epoxy resins, materials of great technical importance used for manufacturing of paints, adhesives, and composites. Both plots are curved. It's the slopes, average slopes close to 0.5 or even less. That means we can expect both samples to be branched, and they are not identical. The red one is more branched than the blue one. And this is nice example again for investigation of conformation of biopolymers. Dextran again. We have Mark-Houwink-Sakurada plots for 3 samples of different molar mass. The green one is the molar mass is partly below 10,000, and the slope is 0.5. So again, we have combination of small oligomeric molecules without excluding volume effect, and also probably some branching for higher molar masses. So the slope is 0.53. Then we have middle molar mass sample in blue. The slope is slightly lower, and the plot becomes slightly curved. And the low slope at this molar mass range already indicates branching. And the sample in red with the highest molar mass, the average slope is about 0.3, and the plot is markedly curved. That means that this indicates high degree of branching for this sample. And the last example is for 3 protein samples. You can see the plot of hydrodynamic radius versus elution volume. And immediately we can see the different elution volume for the 3 proteins despite their almost identical molar mass. That means that actually the conventional size exclusion chromatography with column calibration would provide different molar mass, which is not true. And then we can see different elution volume. So the elution volume of the blue sample is slightly higher compared to the green one. And indeed, the hydrodynamic radius is lower. That means that it corresponds to separation mechanism by steric exclusion. And then we have red sample. It's even higher elution volume, but the hydrodynamic radius is the highest from the 3. That means that we have evidence of non-SEC elution behavior, probably enthalpic interactions with the column packing. Now, if we look on the hydrodynamic radii obtained by online DLS, dynamic light scattering, and online viscometry, we can see that DLS actually has that high uncertainty that all proteins have identical hydrodynamic radius within experimental uncertainty. So basically, we would have to consider all results to be identical. If you look at uncertainty from online viscometry, it is extremely low. That means that now we can differentiate the difference in radii of the 3 samples. And now I give over to Steve back for conclusions.
Well, thank you, Stepan, for a nice exposition of some of the things you can do with viscometry. So what we've tried to tell you today is that improvements in measurement, people have done viscometry for quite some time, but we've made substantial strides in improving the sensitivity and the accuracy of the results. And it really allows you to push the application down to measure hydrodynamic radius of viscometry down to 1 nanometer or even below. Of course, the Mark-Houwink-Sakurada plot provides a tremendous amount of information about polymer chain and polymer chain conformation and branching. The universal calibration, the traditional SEC with viscometer and concentration detector, is a mainstay technique that people have used for many years. It measures molar mass, but it does not compare that well to multi-angle light scattering. And so there's a tremendous power by putting all of these techniques together. So doing size exclusion chromatography, measuring intrinsic viscosity with a viscometer, and measuring molecular weight and size from multi-angle light scattering. Not only does this give you accurate molar masses, but it gives you accurate hydrodynamic radii. And viscometry, in some sense, is a complementary technique to online dynamic light scattering because they both measure hydrodynamic radius. But viscometry really shines when you're looking at small molecules. You get superb accuracy and very good resolution, and it allows you to determine or resolve the differences of very small changes in molecular conformation and size. And so this can be used for many applications, including characterizing proteins and polymers, even when there's column interactions. So thank you very much for your attention. I hope you found this illuminating to talk a little bit about what you can do with viscometry and how the hardware and instrumentation works. And now we have some time for questions, and I'm going to return the webinar to Trevor. Thank you very much.